Hey Fizz Kids, Mr. C here, and today we're going to continue to talk about impulse and momentum, and we're actually going to talk about collisions specifically. So we're going to talk, I know earlier today we did that collision lab, and we're going to talk a little bit more about collisions and sort of the math around collisions. So during a collision between two objects, the forces between the two masses are equal and opposite. So like in this case, the force that A exerts on B, it's the same magnitude but opposite direction of the force that B exerts on A. And the time of interaction is also the same. Like the collision takes the same amount of time for block A as it does for block B because it's the exact same collision. So it has to take the exact same amount of time. This means that the impulse in this case is going to be the same magnitude in opposite direction. So that we know anytime we have a collision now, we know that the impulse of block A is equal to negative the impulse of block B, which is pretty cool. This also tells us that the change in momentum for block B is equal to negative the change in momentum for block A. And if we wanted to sort of rearrange that, because we know that the change of momentum for block B is going to be PBF minus PBI is equal to PAF minus PAO. If we arrange this in such a way so that we have all of our initial momentums on one side of our equation and all of our final momentums on the other side of the equation, we get this here, and this is just a fancy way of saying the law of conservation momentum. All this means is that the total momentum in an isolated system, and we're going to talk a little bit more about what that isolated system is, but the total momentum of an isolated system is constant. That means it can't change. So interactions within the system don't change the total momentum. So that means whatever momentum we start with in an isolated system has to be the same amount of momentum that we end with. So like in this case, whenever we start here, the momentum that we have before the collision has to be equal to the momentum that we have after the collision. So, I mentioned just a bit ago that the total momentum of an isolated system does not change. Well, what is an isolated system? An isolated system is just a system where there is no net external force acting on the system. So we can't have external forces. Anytime we have an external force acting on our system, that means it's not an isolated system and we cannot use conservation of momentum. External forces are any force from agents outside of the system, and they can change that. So, like, if your system is a box and someone's pushing on the box, but that person pushing on the box is not a part of your system, the push on the box would be an external force, and that means that that system is not isolated, and we could not use momentum or conservation of momentum to solve that problem. So whenever we solve problems, our goal is we want to choose a system where momentum will be conserved. So like, let's say we have this system here. We have our friend Bob is on his skateboard. He's pretty cool. He's pretty excited. If we just choose the system to be Bob, there are external forces acting on the system. We have this force of friction that points from between Bob and the cart, and that force means that the system is not an isolated system and there will be a net force acting upon this system. So it would not be a good system to choose if we wanted to use conservation momentum. However, if we choose the system to be the person and the cart, so this whole thing, so Bob, it says cart, I assume it's like a skateboard. Who just like rides carts around? I don't even know anymore. But anyway, the net force would be 0, and in this case, the momentum would be conserved. And in this case, we are neglecting friction between the cart and the ground. But whenever we choose this whole system, there's no external force acting upon our object, which means we could use conservation of momentum in order to solve for this problem, because this would be an isolated system, because as we see from our free body diagram, the net force is equal to 0 here, which is what we want. So how can we solve problems like this? Well, let's look at this. The example of a collision between two skaters. So we know that an 87-kilogram skater collides with a 22-kilogram skater who is initially at rest on the ice. After they collide, they're sticking together, and they move with a velocity of 2.4 meters per second. So we want to find the velocity of the skater B before the collision. So what velocity did he have as he ran into this other skater? So we're going to use conservation momentum. So we're going to choose our system to be the two people. There's no external forces acting on these people. So if we look here, we say, well, let's see, we know that our initial momentum has to be equal to our final momentum. And initially, we have the momentum of person A plus the momentum of person B has to be equal to the final momentum. But the final momentum, they basically run into each other and they stick. So it's actually just the momentum of A and person B, because now they're together as one. From here, we know that momentum is mass times velocity. So it's mass of A times the initial velocity of A plus the mass of B times the initial velocity of B has to be equal to the mass at the end, which in this case is the mass of person A plus the mass of person B times the final velocity of the two people as they stick together. This term here actually goes to 0 because our person A is initially at rest. Skater A is at rest. So she has, in this case it's a she has no initial momentum. So if we wanted to rearrange this equation, we want to solve for VF. We know that our final velocity in this case is going to be equal to the mass of person B times the initial velocity of person B, all divided by the mass of person A plus the mass of person B. And that would be the final velocity of our two skaters as they're moving together. I'm not going to go ahead and plug in the numbers, but if you want to, you're more than welcome to go ahead and plug in the 87 kilograms, the 22 kilograms, and the 2.4 meters per second to figure out what the velocity of the skater would be. Another thing that can happen is whenever we have collisions, but we also have explosions. And explosions is when a particle of a system moves apart after a brief and intense interaction. So usually like if something were to explode, there's that brief force where it's very intense, but then after, the force of the explosion happens, after the two parts in our simulation started, after they exploded outward, they were moving at constant velocity. An explosion is the opposite of a collision. I just had to write that down just so you didn't get confused. And the forces are internal forces. If the only forces are internal forces, then total momentum is conserved. And in this case, initial momentum and final momentum must equal to 0. Why, you ask? Well, in an explosion, things are typically, they start at rest. So if we look in an explosion where we start at rest, then we know that our initial has to equal to our final. And if our initial is 0, that means our final momentum has to be 0. And you might say, well, that means nothing is moving. Well, not necessarily. Because remember, momentum is a vector. So if it was an explosion, maybe some things are moving to the left and some things are moving to the right. And the net momentum might be 0, but that doesn't mean that the individual momentums of each particle in the explosion have to be equal to 0. So make sure that you remember that. So like this would be 0 would be equal to the sum of all of the final momentums of each particle has to be equal to 0. So kind of back to collisions. One type of collision is actually a special type of collision, is what we call an inelastic collision. And there are two types. There are elastic collisions and there are inelastic collisions. And there very rarely are perfectly inelastic collisions or perfectly elastic collisions. Usually it's a combination of the two. However, if you have a perfectly inelastic collision, that is when the two objects stick together and they move with a common final velocity. So like in this case here, when the two cards stick together perfectly, they don't bounce off each other at all, but they stick together and they move and they roll forward with one final velocity. That would be a perfectly inelastic collision. Or in this case, whenever you have your block here in the bullet, when the bullet hits the block and they move together with one final velocity and the bullet is embedded within the block itself, that would also be a perfectly inelastic collision. So anytime it doesn't bounce off and they perfectly stick together, and they have a common final velocity, that means that it is a perfectly inelastic collision. So I want to go through another problem here talking about collisions and explosions and whatnot. So in this case, we have a 30-gram ball is fired from a 1.2 kilogram spring-loaded toy rifle with a speed of 15 meters per second. What is the recoil speed of the rifle? Well, In this case, we want to just look at the system, and this is an explosion because we're starting from rest. It's an explosion. It's the opposite of a collision. And if we look at all the forces acting upon the ball, in this case, they're all internal forces, which means that they don't actually change what the total momentum of the system are, because it's all just forces happening within the system itself. So like if this whole thing is our system, yeah, we have some forces acting in there, and there's a net force for a short period of time, but because they're all internal to the system, we can still use momentum. So in this case, we know that our initial momentum is equal to our final momentum, or the initial momentum of the rifle plus the initial momentum of the bullet has to be equal to the final momentum of the rifle plus the final momentum of the bullet. In this case, both of these are actually just zero because they're both starting at rest. That means that the final momentum of the rifle must be equal to the final momentum of the bullet. So what do we want to find out? We want to find out what that final velocity is. Well, we know that the mass of the rifle times the velocity of the rifle has to be equal to there's a negative there, to the mass of the bullet times the velocity of the bullet. So if we wanted to figure out what the velocity of the rifle is, we can rearrange this equation. We find that's equal to negative the mass of the bullet times the velocity of the bullet, all divided by the mass of the rifle. And I'm going to plug in numbers for this one and give you just an idea of what the recoil speed of this would be. So I would take 0.030 times the velocity of the bullet, which is 15, divided by the mass of the rifle, which is 1.2. I find that my recoil speed is 0.375 meters per second, which is actually a pretty small velocity. And this is sort of a note. And with this explosion, even though the speed of the bullet is very, very fast, because the mass of the bullet is very, very small, that means we're going to have a relatively small final momentum. And that means that because our rifle is so massive, the recoil speed will be small. So if we got a really, really big recoil speed here, that would mean something was wrong probably. Somebody didn't do something quite right here. It's the same sort of thing like whenever we have the forces are equal and opposite and you had a big mass and a small mass. Well, the big mass is going to experience a really, really small acceleration, whereas the small mass will experience that very large acceleration because the forces have to be equal. Well, that is all I have for you today. I will see you in class tomorrow where we'll talk more about conservation of momentum.